So welcome everyone to Guided Study Group week 6 of Math 141. So last week we cover I think indeterminate forms and sequences. So this week we're gonna go more into series. That which is going to be I think like 70% of midterm 2. So before I can do anything, let me note down the email again. 15196. You mean like posting of the link? Cause I talked to Dr. Kasher and we agreed that we're just gonna put every videos in my YouTube channel, so she doesn't have to record it. She doesn't have to post the link every time. So you guys can just look at my playlist that I have Math 141, Summer 18, and you guys can just click on that, and then that's gonna be the place. So you can find. So where do you guys usually look at my? Alright, I'll send out an email again. I think I sent it out earlier before that, but I'll ask her to. I'll send it out again. I'll send an email out for my channel. Okay, cool. So we're gonna get ahead and get started. So today we have 11.2 and 11.3 and 11.4. So quite a lot of things. So let's get started early. So series compared to sequence is much more complicated, and the kind of like the general definition of series is that when you have a sequence, the series is just the nth sum of like some of the terms in the sequence. So say if you have from AN to A1 to A10, then S1 is going to be A1, S2 is going to be A1 plus A2. And so the definition of a partial sum is that Sn is going to be the nth sum of the sequence. So yeah, it's a list of number with additional operation between them, and this series is convergent if limit of n approaching infinity of Sn exists. Then you're gonna have that one is called a convergent series. The distinction between a sequence and a series is that you have sequence is just a list of number. It can have a rule, it can choose to not it can have no rule at all, and the terms doesn't have any additional operation between them. They might just depending on the term previous to them or depend on end, but they will not be like adding of any terms in front of it. And the end sum is just going to be like S1 is going to equal A1, S2 is A1 plus A2. So all of these sum are equal to one another, and no, one of these sum are like the sum of all of the terms in the sequence corresponding to whatever value of your n is. We also have some properties of series. If you have the series of AN and series of BN are convergent series, then you have their sum are going to be the individual sum of the series. And then if you have like AN is also a convergent series, then a scalar multiple of that is going to be the scalar multiple multiply the sum of that series. Then we have some special series, so we must know they're convergent, and that like it's going to be trigonometric series. So I kind of like talked through this a little bit last week, where we have this series of AN equal to R to the N. So this is similar to that. Every single term, say the sequence is going to be AR squared, AR cubed, until RA multiply R to the N minus 1. Now, if you have all of these together, add all of these together, that's we have the trigonometric series. So this sequence is going to be convergent when you have the absolute value of R is smaller than 1, and the absolute value of R bigger than equal to 1 is going to be divergent. Now, And then this is going to be the sum if it's convergent. Now this one has when it comes to like actual series, all you care about is that what is A and what is R. You don't need to put it in this specific form like A multiply R to the n minus 1. As long as you can identify what is R and what is A, like R is just the factor difference between the terms and A is just the first term in the sequence, in the series. Yeah, so like that is, as soon as you understand that part, and then you can easily apply it. So A will always be the first term. And how you know it's the first term is when you plug in this n equal to 1 into the formula of the sequence of the thing here. And R is just a factor. So you don't need to remember this formula as long as you understand what is the meaning of A and R. Then you can use it easily instead of trying to put it into this specific form, which is not necessary. We also have telescopic series. So it's kind of like the series where nearly every term cancels with either the terms before or after that. So it gives us something like a methods of differences. So say if you have a series, say an equal to tan inverse tangent of n minus inverse tangent of n plus 1, something like that. So when you have this series, it's going to be inverse tangent of 1 minus inverse tangent of 2 plus inverse tangent of 2 minus inverse tangent of 3. So you're gonna continue doing that, and you're gonna see every single term in the middle will cancel out, and eventually you're gonna just have inverse tangent of n plus 1. Inverse tangent of 1 minus inverse tangent of n plus 1. We also have harmonic series. Oh yeah, and then telescopic series, it can be convergent, it can be divergent, depending on what specific series that you're having. Harmonic series is divergent, and it's in the form of 1 over n. So if you see like 1, 1 over 2, 1 over 3, 1 over 4, this is a divergent. This is like an important thing to note because later on when you learn about P series, I think I also mentioned it somewhere here, but I have no idea where it is. So we're gonna learn about P series in the limit comparison test. But anyway, this one is divergent. When we learn the limit comparison test and also for the alternative test that we're gonna learn next week, we're gonna see there's a special case where you have, if you have the series of -1 to the n over n, that one is actually a convergent series. We also have some theorem saying if you have this series is convergent, then limit of n approaching infinity of a n approaching 0. So therefore, from here, you can have the test of divergence. It's saying if you have the limit of n approaching infinity of the terms, the n term in the sequence, different than 0 or does not exist, then the series is divergent. Now, this is thing to be careful when you have limit of n approaching infinity of the an term equal to 0. This thing does not leading you to the series convergent. They don't lead to that. Look at the theorem here. It's only if and then. It's just a one-way conclusion. You cannot go the other way around. So let's start it with the first example. So we have find the n partial sum of that series. So I kind of like go through it earlier. So we're gonna get started with all of the terms. So you have inverse tangent of n minus inverse tangent of n plus 1. Now if we expand all of the terms out, so you're gonna have inverse tangent of 1 minus inverse tangent of 2. This is a tangent plus inverse tangent of 2 minus inverse tangent of 3 plus blah 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 until you have inverse tangent of n minus 1 minus inverse tangent of n plus inverse tangent of n minus inverse tangent of n plus 1. Therefore, you can cancel this thing out, and this term will be canceled out with something before that. So you have these things cancel out. Essentially, what you have left is inverse tangent of 1 minus inverse tangent of n plus 1. Now, this sum is equal to this, as this one is where limit of n approaching infinity. Now, when you have inverse tangent of 1 is pi over 4. Remember, this inverse tangent, so you have the domain and the range, and this come back to the material of midterm 1, where you find this angle, and it has to satisfy the range of inverse tangent. So it can only be between negative pi over 2 and pi over 2, not including the two endpoints. And then as n approaching infinity, yeah, it's negative pi over 4 in total. So you're gonna have this one is going to be as n approaching infinity, this part approaching infinity. And if you remember, inverse tangent of infinity is pi over 2. You can remember the graph or just like try calculator and all of that. So it's gonna be negative pi over 4. So that's the answer for this. So just like a way to show you guys how to deal with telescopic series. So try to write down all the terms possible. If you look at a very strange series, try to write down more terms than regularly, and you're gonna be able to see some terms cancel out. In some cases, there'll be 2 terms left at the beginning and 2 terms left at the end. Those things you cannot cancel out. Then you're gonna take all of them and start to like use every knowledge that you learn maybe about like inverse function or anything like that to solve it. You will have a second example. Yeah, telescopic series. This one is, what were you trying to say? Okay, so this one, find n partial sum of this function, this series. So we have here 3 to the 2n minus 1 plus negative 4 to the n over 10n. Now, currently I'm thinking of splitting this fraction into it, because honestly, when I look at the numerator and the denominator and find the series of all the thing, then I have no idea. So I will gonna think of splitting them, but to split them into 2 different series, each of them have to be so I have each of them have to be convergent. So you have 3 to the 2n minus 1 plus negative 4 to the n over 10 to the n. Then I'm trying to split them into 2. And 3 to the 2n minus 1 divided by 10 to the plus. In the meantime, can someone open up? No, not this. Yeah, you guys don't need to. I'll send out an email again. Don't worry about it. So I'm looking at these, and if I want to put an equal sign here, each of them have to be convergent. So I'll check each of them. So you have 3 to the 2n minus 1 over 10 to the n. Now this one give us, so you have the series. So you have 3 to the 2n minus 1. I'll split it into 3 to the 2n, 10 to the n, then 3. So take this negative 1 down. And then 3 to the 2n is just another way to say 9 to the n. So you have 9 to the n and then 10 to the n. So I'll combine them together. Multiply 1/3. Now, what happened is that here you have, this is a trigonometric series. This is the factor. So r is equal to 9 over 10, and the absolute value is smaller than 1. Therefore, I have, this is a convergent series. And then you have another one is negative 4 to the n over 10 to the n. And clearly, you can put them all into the power here, which is also smaller than absolute value of r be 4 over 10, also smaller than 1. So this is also convergent by trigonometric series. then you can find their sum using that formula of A over 1 minus R. We remember here A is always the first term in that series. So you plug in n equal to 1 and find what it is. So you plug in n equal to 1, you're going to have 9 over 10 multiply 1/3 divided by 1 minus R, which is 9 over 10. So this is going to give us 3 over 10 divided by 1 over 10, which is 3. And then here you're going to do the same thing. You plug in n equal to 1, which is the first term, is going to give us negative 4 over 10. 1 plus 4 over 10, because negative with negative is a plus. They have negative 4 over 14. So because both of them are convergent, you can put an equal sign here, and then each of them individually has already been found, which is 3 minus 4 over 14, which is going to give us 42 minus 4 is 38 over 14. Let me see. What do you multiply when you multiply? Oh, so as I say, the meaning of A. So look at here. The way that you put it here is R to the n multiply A, multiply something, right? But in the formula to use exactly the way that they say it, so the formula here is so the formula here is that you have A multiply R to the n minus 1. This one is going to equal A to the 1 minus R, right? But the meaning of that is that A is the first term in the sequence, in the series, and R is a factor. So as long as you can make sure that A is the first term, which means you plug in n equal 1, the first n that your series start into this, then you're gonna have what is the value of A here, and this is the value of R. Look at here, the way that you put your series is R to the n multiply B. But if you want to use exactly what they're saying here, you have to have A, which is going to be B multiply R minus 1, which is exactly what I'm doing here. I put 1R, which is right here, into it. So that's why I'm saying don't try to put it in the form and like use exactly what they say, as long as you can make sure that the A that you're using is the first term in the series by just plugging n equal to 1 into your formula and then 1 minus R in the denominator. Then you're gonna do it. Then you're good. What if each terms are divergent? Then you don't even need to check each term. As long as you can find one term is divergent, you can immediately conclude the fact that your series is divergent. All good? Technically, you would say the series, the smaller, like the complementary are divergent, is divergent. But for the big one, you have two conclusions that you can make. Either you can immediately conclude it's divergent, or you can say this one is not like you cannot find it based on the knowledge that you guys have. So how would we? I mean, if it's divergent, there's no sum. Like divergence, it's not leading you to a number. It's leading you to either infinity or negative infinity, right? There's no way you can find it. What did you multiply by 1/3? So 1/3 here is when you plug in n equal to 1, right? Whatever this entire factor equal to. So it's 9 over 10 multiply 1/3. So 1/3 is just your b here. Do you see what I'm saying? So the 1/3 here, you try to put it into this form. You have A is going to equal B multiply R. So this B is 1/3. So this is what you're trying to put here. Basically what I'm saying is that just plug in the first value of n into this entire formula. This is going to be what you have in the numerator. And then 1 minus R, with R as a factor, is going to be in the denominator. Is it necessary that the sequence will be in the form of GP? What is GP? And is it necessary that the sequence will be in the form of? I have no idea what geometric progression is, but I mean, it doesn't necessarily you have to put it in the form as long as you can. The way that I write it here, it just allows you guys to find. Yeah, like the way I write it here just allow you to find what is R and what is the fact that you have to multiply to it, like say some extra thing here that you have to multiply to find the first term A. I don't quite understand what you're asking. Like, is it necessary that the sequence will be in the form of geometric series always? I mean, what do you mean by that? Like, the sequence can be in any form. It doesn't have to be geometric series. But the geometric series is like the one that we have a set formula to find the sum of the series. You see what I'm saying? Yeah, that is true. Yeah, we can only use that for geometric. For other form like telescopic, you have to write down the terms and see if anything cancel out and what you have left. And as I say, for telescopic series, it can be divergent or convergent. Yeah, and harmonic series is always going to be divergent. Okay. So one more thing is, I think Kevin, did you? No, not Kevin. Calvin. I mean Calvin. Did you actually understand why I have to multiply 1/3 now? Um. Okay. Cool. So we're gonna go to the next example. Given that the series is the sum of like this, the n partial sum of that series is 2017. What is the limit of n approaching infinity of that? Now this one is where we use one of the theorem when we have. So look at this here. The series is equal to a number. What does it mean by that? It means that the series is -1. Not quite. Yeah, I think you're getting there, but anyway. So the series is convergent, which means that it's going to give you limit of n approaching infinity of an is going to equal to 0. So the n term in the sequence is going to be definitely 0. That is a theorem. And so you're going to apply this one to solve the thing here. So you have limit of n approaching infinity, cosine of 2an minus 3 divided by 2an plus 3. So you're going to have cosine of 0 is going to be 2 pi or 0. Oh no, cosine of 0 is, yeah, 2 pi. I think so. Is it 2 pi or is it 0? Cosine of 0 is 1, honestly, sorry. Cosine of 0 is 1. 1 minus 3 divided by 2 multiplied 0 is 0. 3, so it's going to be negative 2 over 3. Confused myself. It's going to be negative 2 over 3. So is it clear here that how I get this? So I just try to show you guys one of the way that you might be asked to use the theorem that we have. Like if a series is convergent, then the limit of n approaching infinity of the n term in the sequence is 0. So if we don't have any questions here, I'll go to session 11.3. Oh, we still have one more. Yeah, this one is going to be the quicker ones because this is going to use all the series that we've learned so far. I think I include in here telescopic series and also geometric series as well. So we have, I think this actually include everything we have in section 11.2. So here, it's asking which of the series is converges. So you don't need to find a sum or anything, you just need to determine if it's convergent. So here I'm going to rewrite this one. Usually the way that you to notice is that when you have something to the power of n or n minus 1, it kind of like give you a sense that you might need to put it in the form of geometric series. Here I'll write down is 3 to the n divided by 4 to the n multiplied 3. Just like try to put it into the form of power. Then you're gonna have is 3 over 4 to the n multiplies 3. So the factor is 3 over 4. Therefore, r is equal to 3 over 4 smaller than 1. So it's a convergent series. Now for b, you have this series 2 over n squared minus 1. Now this one, I would say the hint here is look at the denominator, because like the numerator is just a constant. It doesn't really give you whatever it is. Therefore, you're going to have that one. I'll try to factor out what is the denominator. And this is going to be 2. We use. Oh, you don't need to find the sum. It's just asking if it's convergent or not, right? Is this which of the series is convergent? It doesn't has yeah. Don't assume the fact that once you have geometric series you have to find the sum. I mean sometimes it's helpful to find it, but not necessarily. Especially I think in the exam, there's some of the question that is just asking you if it's convergent, divergent, or absolutely convergent, or conditionally convergent. So you don't need to answer that part. Anyway, you're gonna continue to factor the denominator here. So it's n minus 1 multiplied n plus 1. Now this one is where you try to use partial fractions. Why am I saying it is that you try to like just put this into two fractions. And then you have 2 n minus 1 n plus 1. If you use partial fractions for this, you're gonna have it's gonna be a over that plus b over that, which is going to give us 1 over n minus 1 plus minus 1 over n plus 1. That's like if you do the algebra. I don't want to do the algebra here, but it's pretty self-explanatory. And that's how we come up with a geometric series. Give me a second. What the heck is wrong with those people running in the floor? Yeah. I don't think it's divergent though. Hang on. So if you write down the terms here, you're gonna have there's gonna be 1. Oh, it should start from 2 and not from 1. Sorry, starting from 2. Pretty messy here. Yeah, I also have someone video just keep popping up on mine. Give me a second, I'll check on the participant. Oh, actually what happened is that now we have 10 participants, which I have no idea why. But so for Lizzie, can you please put in your PSU email in the chat room? Anyone who just joined us, like app he carry, can you also put in your PSU email in the chat room? Thank you. Somehow I saw free Lizzie in the group, which is not really understandable. But anyway, I think what happens is just like whenever someone joins us, then KHM. You don't need any email. I just note down your email for my purpose of attendance. But the email, if it was sent out, it will be sent out to everyone on campus. So yeah, I didn't send out any email last week. That's why you didn't receive an email. But cool. I'll try to send out an email to everyone in the class today about the change in the video posting. So I'll let you guys access to my YouTube channel or not access, but like, yeah, see all the video I have in my YouTube channel, and so you guys can find all of the video there. Yeah. No, I don't send out review problems like just for the people attending the group. It's gonna be for the entire class. There's no, yeah, that's gonna be discrimination. But anyway, yeah. So true. Yeah, you guys don't need to put your PSU email. Like whoever already gave me at the beginning, you don't need to. It's just the two people who just joined us, like Lizzie and Apia. But she or he just sent me, so that's good. We only need Lizzie more. But anyway, Kevin, I think A is 1 and then B is -1. But when you write down the terms here, it's starting from 1 minus 1, 1 over 1 minus 1 over, it's starting from that 3. So you have plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5. So you can see essentially 1 over 3 and 1 over 3 is going to cancel out, and every terms with 1 over 4 minus 1 over 6, 1 over 4 is going to cancel out. So what you have left at the beginning is going to be 1 over 1 plus 1 over 2. And then when you do it essentially to the end, what you have left is also going to be 1 to the something plus n minus 1 over n plus 1. So this is why you have n. You have n minus 1 before the n minus 2. This is going to be n minus 1 plus 1. So it's going to be n. So if you write down more terms here, you're going to see the fact that these are the only two terms left in the series. So what you end up having is that you're going to have 1 plus 1/2 minus 1 over n minus 1 over n plus 1. And as n going to infinity, then you're gonna, hold on, I think Lizzie has a problem with connecting. I think her PSU email is a little bit weird. Can we use relative rate rule to 1 over n squared? Yeah, we can definitely do that. Can't we find the limit of given the questions and the limit of the given questions and see if it equals 0? I mean, as I say, if you find a limit and it's not equal to 0, and in fact here the limit, if it's equal to 0, you cannot conclude anything. If it's different than 0, you can use a test of divergence and say it's divergence. But here's actually it's a convergence series. If you can let me continue for a moment, then you're gonna find this one is equal to 3 over 2. Because at n approaching infinity, these two terms equal to 0, and these two terms add together is gonna be 3 over 2. So that answers Sivanji's questions. Can't we use the relative rate rule to 1 over n squared? Yes, you can definitely do that, but I haven't got to there yet. It's in section in the comparison test. So yeah, we can also do that. Here I'm just trying to like show you a way that it is a telescopic series, but it is masked under something else, and you have to use some techniques to break it down. It's 1 over n is divergence. Nope, that is the p series. The p series say 1 over n is divergent, but 1 over n squared is convergent. So 1 over n and 1 over n squared, as n approaching infinity, what does this thing go into? This one is going to 0, and this one is going to 0. So you can ignore them, and what you have left is 1 over 1 plus 1 over 2, which is 3 over 2. Okay. Yep, and I would say I don't think the exam is going to be to this point, but definitely this is the extreme of what you guys can be asked. And I think based on what I look at Dr. Kasher did this year, I think the math department and everyone wants us to include more things. So I feel like last summer was actually quite easy. And then this time they're making it a little bit more intense because they try to cut out a lot of materials last time and now just putting everything together because it doesn't feel like the student actually understand all of the aspect that they should be. So I'm just including all of them here just to make sure that you guys get a chance to see telescopic series. So it's convergent, yes. So this is convergent. Now we're going to C. So C, I think Sivanji is gonna know how to do this, where you take the limit of n approaching infinity. So this is where I'm trying to say, C, you can try to do partial fractions. Just tell you the fact it's not leading you anywhere. But that's a trial and error thing, and this is just your few first step through the sections. So don't freak out about like how do I know what I'm gonna use. Well, the thing is, you have to go through all of them to know what method you're gonna use. So you have limit of n approaching infinity, k squared. So this is the first thing, and I know how the fact that I have to do this is where you look at the fractions, and honestly I have no clue how to break it down smaller, but the k squared and k squared give me a sense that maybe if I find this limit, it's going to give me a number which is not 0 because the biggest powers equal to one another. So this one is giving us 1 and this is different than 0. So you can use test of divergence and give it and say that this is divergent. Do you see what I'm saying? It is easier to use p-series. That is true to use p-series, but what if the question's asking you, well, don't use p-series and say, and even if you use p-series, you can say if it's convergent or divergent. But what if they ask you to find the sum, right? Then you should be able to see that there's telescopic series here, right? You mean k to infinity? Yeah, k to infinity. So, all right. So we have D. So there are so if you think about it, right, the comparison test, the limit or like the direct comparison test doesn't really matter. It only tells you like all the tests that we learn. It only tells us if it's convergent or divergent. But by doing these telescopic series and geometric series allow us to actually find the sum. So if you think about it, like if the question is asking you to find the sum, you can use only geometric series thing or telescopic thing or maybe some other special thing but not relating to the test. But if asking if it's convergent or divergent, you can use like integral test, comparison test, direct or limit, all of that, right? So also, what is the theories? Yeah, test of divergence. Yep. I'm just like rewrite it, and you're gonna see like from now to the end of, I think, term 2, and I'll have a lot of abbreviation because I don't want to write down like, okay, alternative series test or like limit comparison test and all of that, right? So that is A, B, C. You have D. Well, D is pretty self-explanatory, right? This is a geometric series with a factor of sine 100. Sine 100, regarding of what its value is going to be always between -1 and 1. And I know the fact that the equal sign is not here. Sine 100 is definitely not 1 or not -1. Therefore, we have this is a convergent series by geometric series. And then for E, here you have 2 different series, but you can break it down and try to break it down, but you have to identify each of them individually first. So 2 to the n, and then you have 2 over e to the n and 4 over e to the n. Now if you look at these, the first one is convergent because 2 over e is smaller than 1, but 4 over e is bigger than 1. So this one is divergent. Therefore, you have the entire series is divergent. So this is where but this one is convergent. So this answer one of the questions that someone raised up before, like what if one of them is convergent? What if one of them is divergent? You see what? Do you see what I'm saying here? Okay, cool. Now we're gonna go to 11.3 integral test. So there was a lot of things to cover in the 11.2, but I think it's good practice. Now integral test is pretty easy in the concept, but actually to apply it, I would say in all of the tests for series, integral test is the hardest to do because they have a lot of conditions that you have to satisfy, and the fact that you have to find an integral is not really fun because it means that you have to do double the work. But yeah, I would say in the exam with the time restraint, I don't think you're gonna have that many integral tests, but definitely there will be some questions that have it in there. So integral test asking, suppose f is continuous, positive and decreasing function from b to infinity. So you need it to be continuous, positive, and decreasing. And then you have that series is convergent if you have, say, an is put into the like some function of n, then you have it's convergent if the sequence if the integral from b to infinity of fx is convergent, and it's divergent if that integral is convergent, it's divergent. The note here, even though you find the convergence from here to here, they are not equal to one another, which means an is not equal to b to infinity of fx. So you find these, but they are not equal to one another. They just have some association that if one is convergent, the other is convergent. But do not make a mistake thinking that they are equal. We also have p series, which is we already learned. It's the series of 1 over n to the p. If it's convergent, p is going to be bigger than 1, and divergence if p is smaller than or equal to 1. Cool. I think this is pretty self-explanatory. So let's do, I think, example 5, 6. 5 is a long one though, because this is the challenging one. It's asking for what value of p does this series convergence. This one is where we have, so we have the series starting from 3, 1 over n, ln of n to the p. I think the answer that I have for this is p smaller than -3 or so. So here, if you find it, there I will start it with a few values I have, ln of n to maybe the 1 over n. This one we know is divergent. So if it's ln of n to the 0, which is divergent, 1 over n of ln of n to the -1, 1 over n ln of n to the -2, and 1 over n ln of n to the -3. You guys might wonder, why did I just go to the negative part and not the positive part? If you think about it, like, when you try to find an integral, right? 1 over n ln of n to the p. Now, if you have this part, if it's a positive number, so say ln of n to the 1, like this, when you find the integral, right? Integral from 3 to infinity of 1 over n ln of n. What do you have here? If you put ln of n be u, and then you're gonna, and then I think dn. If you have ln of n be u, and then let's write it in another color so that's not confusing people. If this one is u, this one is going to be du. So you're gonna have is equal u du, which is going to give us u squared over 2 from ln of 3 to ln of infinity, right? And clearly this one is going to give us infinity. So what I'm saying here is that when you have p positive and you try to find the integral, it's going to lead us to divergent. especially when you try to use up like with n increase positively, then you're gonna have a bigger and bigger so you're gonna have like u cube or u fifth or those kind of stuff. It's gonna give us divergent. That's why I'm heading towards the negative. Here you try to find 1 over n, multiply 1 over ln of n dn. So if you again do u use up, you're gonna have it's going to be 1 over u du, which is going to give me ln of u, which is ln of n, as n going to from 3 to infinity, and this one is still divergent, so we don't take it. So I kind of like jumped through a quite some step here. So here you put u equal ln of n, then you have the integral of 1 over u du, and that integral is going to be ln of u, and that's going to be ln of n, and that's divergent. Continue if you try to do more square dn. So then we're going to have u to the negative 2 du. Again, this one gives us negative 1 over u, with u going from ln of 3 to ln of infinity, which is going to give us negative 1 over ln of infinity is going to give me infinity first, because minus with minus is a plus, 1 over ln of 3. So this one is leading to 0 as, and then this one, so this one is where we have as convergent. So here most of the step of what we're doing is just trying to find 1 over n ln of n negative 3. Then you're gonna do the same thing. So you're trying to find a value of n that when you find the integral, it's gonna be convergent. Also, when you have those value of n, so say here I have, my answer is that when you have n smaller than or equal to negative 2, you have to check back if it's satisfying the conditions of the integral test. Like here it's continuous, so it is continuous because everything is positive. Then you have, and then you have the positive. I try to make the starting point of n at 3, which is going to make every terms in the by the either ln of n and n be positive. So we also need one more thing, it's decreasing function. So after you get this value of say n equal to negative 2, try to find their derivative and make sure that it's decreasing. So just for this question alone, in the exam, I can write in 5 different ways that you guys can be asked to solve the question. So say if I give you 1 over ln of n, the series of 1 over n ln of n, so p equal to 1, I'm asking you if it's convergent or divergent. I can do 5 different cases here, and if you guys don't have the general rule that we're doing in this exercise, it's gonna take you so much time to figure it out, right? Not just 5 different types. If I run right 10, I can give it 10. And if you guys don't see the general rule, then you guys have to do it like 10 different times of finding integral, right? So what I'm trying to solve here is that this is a general exercise that can be expanded out much more. But if you see the general rule, say n smaller than or equal to negative 2 here, then you're gonna have a convergent. Then you only need to do it once with like a lot of smaller part here, but it's gonna save a lot of time compared to doing each of them fresh. So before I go to the next questions, is there any problem with this one? If you feel like I'm going too fast and need to explain something, that's completely fine. And that you still have to go through all this process. It is true, but this is the first time here, and this is like the practice. So I'm showing you here, so in case you're gonna be asked, because this question is kind of like one of the classic one in integral tests, especially when you only need to find ln of n and then you have to put it in u substitution. So don't expect that the integral is gonna get super crazy, because that's not the point of this midterm 2. It's trying to test how you understand the series. Did you know to go in the negative directions? So as I say earlier, if you have the positive one here, right? Say if you just simple simply put p equal to 1. Then you're gonna see the fact that if you use the u substitution, you're gonna end up with u squared over 2. So when you have u in the numerator here, and you have ln of infinity, it's going to give you divergence, right? It is a positive number, ln of infinity. You have to plug it in. So what you try to do in the negative direction is that you try to put this u to the denominator, do the u sub in the denominator. Then you're gonna have like some constant divided by u as u going to infinity. That is going to suppress it and put it to 0. You see what I'm saying? Nope. There is not fast and easier way to find that number -2. Unless you want to go to like advanced math and programmatic thing, but I have no idea how to do that part either. So yes, but this is only here in the example. So in the exam, you kind of get a sense of what you need to do. I don't think it's gonna get anywhere of this hard, but it can ask you like one of these 5 different options. So say if you've given you the series from 1 over n, multiply ln of n to the -2, it gives you a general, you already did it in the example, right? So it saves you time for that. Yep, and I always say my examples are always harder than the exam, but it always, if you understand what I'm actually saying, then pretty good shape. Yeah, so let's do example 6. Oops. So which series can get their convergence determined by the integral test? So if you look at this here, so to use the integral test, we have the conditions that we have to satisfy. It has to be continuous, positive, and decreasing function. So now let's get started. Oh, change back to the color. So you have A, you need a continuous. So if you look at A, sine 2n and n squared. N squared is always positive. Oh, first of all, you look at it as continuous because sine is defined everywhere and n is positive. It's not going to reach 0 on from 1 to infinity. So it's continuous. But is it positive? You have sine 2n. It's going to fluctuate between -1 and 1 all the time, right? So it's not going to be positive. So this one cannot use the integral test because it's not positive. In the numerator. Numerators fluctuate between -1 and 1. So your fraction is also going from -1 to -1 over n squared to 1 over n squared as well. And actually, if you graph it out, it's going to look something like this. So it's going to fluctuate back and down, but it's not going to be just positive. So you cannot use integral test for A. Now, if you look at B, you're going to, so now you have the series from 1 over n, ln of n squared, starting with n equal to 2. Now, if you look at n equal to 2, the first value of, so you have ln of n squared here and n. So these are all positive, and then it's also continuous. So the thing that you need to check here if it's decreasing. So if it's decreasing or not, you have fn is equal to 1 over n, ln of n squared. And if you try to find this derivative, oops, I was trying to put, oh my god, this is going to be kind of like a massive one. But sure, we can do negative ln of n squared, negative n, and 2 ln of n, 1 over n. But these things gonna cancel out. And this one is going to give us n squared ln of n cubed, negative ln of n, negative 2. So you kind of like cancel one of the ln of n. So what happened here is that n squared is positive, negative ln of n to negative 2 is, so I think to not confuse you guys, I'll start with 2 instead of 3. I mean, if it's start of 2 or 3, it doesn't really matter. Like it's gonna give you it's gonna be usable for integral test anyway, because essentially for integral test, it doesn't have to be decreasing from the first point to infinity. It can, as long as the final train of it is decreasing, then it's going to be good. So if you have n equal to 2, you're gonna see that it's a negative. Well, I mean, doesn't really matter. And when up 2. So when n equal to 2, you're gonna have this one is negative and this one is also negative. But you don't need to care about that first term. Essentially, when n approaching infinity, this one is negative and this one is positive. So you're gonna have f prime of n is going to be smaller than 0 as n going to infinity. Then you're gonna have this one is a decreasing function. So the answer is that you can use integral test for this. Before I go to C and D, is this part clear to you guys? Of how I get to. So the question is asking like which one you can use integral test. So basically you just check the three conditions of each series if it's satisfied, and if it's satisfied, then it's then you can use integral test. So here you just have to check if it's decreasing or not, because it's positive and continuous. Now we have C. Okay. I have little questions. So what is your questions? How did you find the numerator? So it's if you have 1 over u and 1 over, so you have, this is a quotient rule, so you just have n ln of n squared, right? You square the denominator, so you square that, that's ln of n squared, and then you're gonna have, so it's gonna be f prime g minus g prime f. F here is 1, so this part initially is gonna be 0. So basically you just find what is the multiply 1. So what is negative of g prime? And here, back here is going to be product rule. So this part here is product rule. So the first part is already 0, so you ignore it because f is 1. But you have g prime, and g is this entire thing, n multiply ln of n squared. So if you take that from here, you're going to have 2 here, which is product rule. So you're going to have n multiply ln of n squared. Is it clear of how I get it? Okay, cool. So you have C. The series is going to be 1 minus cosine of 2 pi n divided by n squared plus 4n plus 7. Now, this one is kind of like a tricky one because you're going to skip one of the some of the terms. What happened is, when I look at this one, I have no clue how it really looks like. So as I said last week, one of the hints is to write down the terms. You're going to have is equal to so you plug in n equal to 1, and then you see where the term is leading you. So n equal to 1, you're going to have 1 minus cosine of 2 pi, which is going to be 0. And then you have n equal to 2. Oops. And have is equal to 0. You have equal to 2, you're going to have 1 minus cosine of 2 pi. 1 minus cosine of 4 pi is going to be 0. And you have 1 minus cosine of 6 pi, which is again going to be 0. So every terms in this sequence is 0. It's not even positive, honestly. So the hint here is that you don't even need to use integral test. You can say that this one is convergent. But the key point is that you cannot use integral test for this because it's not positive at all. Every term in this series is equal to 0. So it doesn't satisfy the conditions. So for D, the last one, you have E1 over N u over n squared. Now you have is a positive number because e to the something over n squared is positive, continuous. And now you check if it's decreasing. So you have f prime of n is going to be n fourth. This part is going to give me e to n 1 over n. This one is where you cannot use derivative to see if it's decreasing or increasing, but you can use general idea of math. So when you write down the terms here from 1 to infinity, n equal to 1, 2, 3, 4, 5, as long as you can have a hint that is decreasing, then you're good. So you have e, and then you have square root of e over n over 4, cubic root of e over 9, and then fourth root of e over 16. Now what happened is that if you look at the numbers and maybe like use your calculators a little bit, you're gonna see the fact that the numerator is decreasing. So from e to square root of e to cubic root of e to fourth root of e. So all the terms are decreasing. You have n squared is increasing. So you have from 1 to 4, 6 to 9 to 16. Now you have a decreasing denominator, decreasing numerator, and increasing denominator, which is gonna make both of them is going to make the entire fraction decrease strongly because you have a smaller numerator and bigger denominator. Therefore, this is a decreasing function. Therefore, you're gonna have this. You can use the integral test for this. How to take integral of that? You're gonna put u equal 1 over n. You use up here. But generally, this you can use integral test for this, and because it satisfies all the conditions you need for integral test. So before I go to 11.4, any questions here? So for B, can we just do the same thing? Test out the n value. You can do that. Yeah, you can do that. Write down the n values, but I mean, okay. So two ways that you can find if it's a decreasing function. First is you write down all the terms. That is like the way that you can apply for all the sequence. But for B, you can also use what we learned in Math 140, which is the first derivative test. Not first derivative test, but take derivative to see if it's a decreasing function or not, right? You don't have to do the integral here. B is taking derivative, not integral. Right? When you're trying to find if, yeah, you can hate it, but sometimes like in the exam, you wouldn't be able to write down all the terms. So yeah, technically there are two ways you can do it. You can use whatever ways that works for you. But sure things. That is, besides his questions, is there any other questions for this before I jump to 11.4? If not, just go ahead and go to 11.4. So we have comparison test. So comparison test, I would say, is kind of like one of the common techniques that you might need. You're gonna use in the exam, just for the fact that it's very quick to use and it's like easy to understand, and also it's applicable for a lot of series. If you were able to identify one of the series that you already know is convergent. So you have two comparison tests, the direct and limit comparison test. So the direct comparison test is that when you look at a series and you know the fact that it's going to be smaller than or bigger than some certain series that you already know, their convergence. So say here, if you have the series of AN and BN, a series with positive terms, then you have if AN is convergent and AN is smaller than every terms in BN by in the sequence, then you're gonna have This one should be Bn. Sorry, this is the Bn. It's also convergent. The bigger one is also convergent. Wait, hang on. I think I might have written the wrong thing here. It should be Bn here. Yep. If the bigger series is convergent, Bn is convergent, then smaller one, An is also convergent. And if Bn is divergent, and An is bigger than Bn, then you're gonna have An is also divergent. So basically it's saying if you have a bigger series and it converges, then the smaller one will also be restrained and it also converges. On another way, if you have the smaller one already diverged, so it's already blow up, so the bigger series is also gonna blow up. So if just getting small, so if it has something already small converges, then you're gonna have something smaller also converges. And if you have something small already diverges, the bigger one also have to be diverges. Just graphically say. So the thing that you must know here is that you must know the convergence of the series Bn for comparison. So you cannot compare it with some series that you have no idea, like that's not leading anywhere, right? And usually the way that you choose Bn is either P series, geometric series, or you're gonna have rational function, say like rational function, where you can use maybe test of divergence to identify if it's convergence or divergence. So that's what we have for Bn. You're gonna see more when you do I think my practice problems. Let's see my practice problems. I don't have that many here, but we have this one. Okay. Somehow when I copy it from the other slide, it just makes so many formatting problems. But anyway, so we have that is limit comparison test. Direct comparison test. So we have limit. So limit comparison test allow us to like don't do the positive, like you don't need to compare directly the train between the two series. This is allow us to say if you have they kind of like they have the relative rate of growth. So say the limit of n approaching infinity of an over bn is a constant, then when c is finite and bigger than 0, then either both of them are convergent or both of them are divergent. So if you already identify what is Bn, you can use the limit comparison test immediately. And this is, I think most of my students end up using more limit comparison test than the direct one because it's just like easier to use and you don't need to like compare the series. But sometimes taking this limit of n approaching infinity of an over bn can be a little bit tricky. But we're gonna do both, don't worry. So I'm gonna go to example 7. Yep, example 7. Is this series convergent? So the thing with this is that first I'm gonna use the direct comparison test, but you guys can always use this with like a different one. Here the direct comparison test is better because if you look at sine square, the thing with any geometric, not any, just sine and cosine is that they're always going to be squeezed between -1 and 1. Here you have sine square, so it has to be positive. So you have the kind of like the range of sine square is going to be between 0 and 1. Now you add in 3 to get the numerator. You're going to have sine square n plus 3 between 3 and 4, and you divide all of them by 3 to the n, sine square n plus 3, 3 to the n, and then 4 by 3 to the n. Now if you have this series, so you have this series and this series. Now you have both of them are convergent. Why? Because C is convergent, just like CN, CONV. It doesn't really matter, it's just my abbreviation. Because here you have the trigonometric series with r equal to 1/3. If you write the series out, and then this one is also equal to 1/3, and it's smaller than 1, so it is convergent by trigonometric series. So your conclusion is that sine square n plus 3 over 3 to the n is also convergent by direct comparison test. And that is because you compare it with 4 over 3 to the n. If you have this series is bigger than sine square plus 3 over 3 to the n and is convergent, the bigger one is convergent, so the smaller one have to also be restrained and also converges by direct comparison test. So in this case, using the direct comparison test is better because you can slowly identify what is the series which is 4 over 3 to the n. If you want to jump immediately to limit comparison test, it might be a little bit harder to identify what series is it to compare. So before I go to example 8, anyway, 4 over n, 2 is less than 1. No, not 4 over 3. R here is 1 over 3. You look at the series, it's 4 over 3 to the n. This is not 4 over 3 to the n. Do you see what I'm saying? The factor here is 1 over 3 and not 4 over 3, right? So this one, if you write down, is 4 multiply 1 over 3 to the n. Do you see what I'm saying here? I just skipped one of the algebra in between, but yeah, I should have written it down. And here is the same way. This is 3 multiply 1 over 3 to the n. So the factor of n is only applied for 1/3 and not 4/3 here. Yep. Yeah, I think I should have written it out. That'll be easier for you guys. But yeah. Sure. So if it's good, we're gonna go through the next example. So determine the convergence of this series. So this one I do want to do both of them because I want to show you where you can use one you're gonna use direct comparison test, but the other one you cannot use direct comparison test and you have to use limit comparison test. And what happened here is that the first one you have n minus 2 over n cubed plus 1. So just tell me guys, by just looking at it, what series do you think that I should compare it with? This is a good practice as well because as when you try to solve the problems on your own, you have to be able to identify what series you're gonna compare it with. So tell me guys, what do you think that I should compare this one with? There's one answer. Any other answer from the other in the group? I don't say it's right or wrong. I just want to know your opinion. Because I want to make sure that everyone in the group understand what we're doing so far. What does it mean with the hat? Okay. So we have two answers, 1 over n squared and 1 over n cubed plus 3. I would say both of them are correct, but one is easier to use than the other. So for sure, here, you're gonna have 1 over n squared is convergent, isn't it? Yes, it is convergent by P series. 1 over n cubed plus 1 is also convergent if you do one more comparison test with 1 over n cubed, right? So what happened here is that you have n minus 2 over n cubed plus 3 and it's starting from 3, right? So for one thing, you know that this one is always going to be, well actually, if you use, actually 1 over n cubed plus 3 cannot be used, and I'm going to show you why now. So we have two answers, 1 over n cubed plus 1 and 1 over n squared. If you want to use the first 1 over n cubed plus 3, yes, you can do it, but you cannot use the direct comparison test. Why? As n starting from 3. Oops. Right. N starting from 3. N minus 2 is always going to be bigger than 1. So this part is bigger. But you know this one is convergent. So if you want to say that this one also is convergent, then you have to use the limit comparison test. But the limit comparison test will not be helpful here because you have, if you take the limit of this over this, you're going to have n minus 2 over 1, which is going to blow up and give us infinity. So I would say this one should not be used. But it is a good start. So now I'm going to show you what is the starting point that we should be looking at for these things. It's like usually when you have a fraction, and I think you guys have done this a few times, you look at the highest power in the numerator and the highest power in the denominator. You have n here and n cubed. So it's going to give, if you take the ratio of that, it's going to give you 1 over n squared. So if you try to use, you can use limit comparison test here with 1 over n squared, but I will do the direct comparison test first, and then for the second one, that is going to be limit comparison test. Why? If you look at here, n minus 2 over n cubed plus 1, right? You're going to have this one is smaller than n over n cubed plus 3. N cubed plus 1. Because the numerator here is bigger. So, and the same denominator. So n is, so this one is, this fraction is bigger than that. Now this fraction is also smaller than or equal to n cubed, because here the denominator is bigger, so it's going to be smaller than a fraction with a smaller denominator, but same numerator. And this one is just 1 over n squared. So this one is where you use the direct comparison test. And this one, because this series is convergent by p series. So that is where you use a limit comparison test. However, what I want to show with the second series is that you have n plus 2 over n cubed minus 1. You still use 1 over n squared because they still have the same ratio of the highest power in the numerator and denominator. However, you cannot use the direct comparison test because if you do that, you're gonna have n over, you're gonna try to compare, you have to make this one smaller than that, but you cannot do it because if you look at here, I'll go slowly from here, 1 over n squared. This one is bigger than or equal to n over n cubed minus 1, right? Because here you have a bigger numerator, so this part is smaller. Now this one is also bigger than n over n cubed because the denominator here is smaller. So the fraction is going to be bigger than the other one. And this one is equal to that. So actually this part is bigger than your series that you try to say. But if you want to say it converges, this series have to be smaller than 1 over n squared. Remember what I'm saying? If you have a big convergent series, the smaller one have to be convergent. Here you have a smaller one convergent, so you cannot use the direct comparison test. So here you're going to use a limit comparison test. Did you see what I'm saying? It might be a little bit confusing, but this is the case I'm trying to show you. So, oh, sorry, I'll jump back to that. Is it clear to everyone? And Carrie, is it clear that you cannot use 1 over n cubed plus 1? I mean, it is a good start. So now I'm showing you where you're starting from it. So you won't make that mistake in the exam. So there's no point of feeling bad or anything about it, right? It's a good thing that we're learning something. You don't get it? Okay. Which part don't you get it? Then I'll explain it again. Don't worry. That's my job. So how can you tell if it's bigger or smaller? So do you understand the step that I go through here of how to derive this bigger or smaller? I'm trying to like, it's convergent. The bigger the one determines whether it's. So here again I would say kinda, how can you take out the numbers? So first of all, do you understand that we're gonna just look at the highest and the highest power in the numerator and denominator? Yes. Okay. You have. So I think what you don't understand is these two parts of how I come here. So what happened is that when you try to use direct comparison test, right, and you have 1 over n squared convergence, and that's the series you try to compare it with. So if you want to say that this one is, if you want to use comparison test, direct comparison test first, 1 over n squared, then you have this series have to be bigger, because say you think this is a bigger series and this is a smaller series. If the biggest one's convergent, the smaller one have to also be convergent, right? So if you want to use this one to compare, this one have to be bigger than this, than whatever fraction that you're using, if you use direct comparison test. This is why I derived this part, that I show that it is the series that we're trying to compare is smaller than 1 over n squared. That's when you can use direct comparison test. Now, on the other side, we cannot use comparison test because this part is bigger. And I think what you don't understand is that how did I come with these numbers, right? Like n over n cubed minus 1 and n over n cubed. Is that what you don't understand? Okay. So again, which part don't you understand again? I feel like is your cursor like this part? Do you understand this part? So do you understand the two things here? Like, why do I have to make this thing smaller than this? And why do I show you that this one is bigger than this? Like this one and then this one. So here you have this fraction is smaller than 1 over n squared. So you can use the direct comparison test here, but you cannot use the direct comparison test here because you're trying to compare it with a convergent series. But this convergent series is smaller than whatever series that you were given. Therefore, you cannot use direct comparison test. But you have to use limit comparison test. Do you see what I'm saying? So what I'm trying to show in this exercise is that for the two series that look really alike to one another, one you can use direct comparison test, but the other one you have to use limit comparison test. Okay. So are we good here? Or you need more explanation? You can try plugging in numbers. Can you do the LCT? Both of them you can do the LCT, but one of them you can, but only one of them can use the DCT. So the LCT, I would say, is more general than the DCT. If you want to use it all the time, that's completely fine. It is a multiple choice test, so they wouldn't ask you to write it down. But I just want to make you guys see the difference. But don't freak out if you don't understand this exercise, because it's kind of like showing the entire pictures of comparison tests. But you can use so DCT and LCT here. Yep. So if we all good here, and no more questions, this is a practice questions. Again, I'll send the slide to Dr. Kasha and also send the slides to you guys through. I'll send the link to my YouTube channel through emails. And so that's all we have for today. I apologize if it's a little bit too much for you guys. Feel free to let me know if you have any other questions if you review the slides at home during the week. Yeah, that question's finished because it's just asking us determine the convergence, and you can see the fact that you can use the test with it, and a series is convergent to compare, right? So a very clear answer is that it's convergent. How do we get a solution to your praxis problems? I do not do it. I do not have a solutions for them individually, but try to solve them and see if you have any questions anywhere. I'll let you know. Because most of them are taken from my previous quizzes. So I don't have a specific solutions for like a written down note, but if you need any of them, let me know. Okay, so first of all, with Kelvin first, don't you do the sub n divided, do the a sub n divided b sub n? Yeah, I mean, you can do that. It's just gonna give you 1. It's positive. So let me do that. So we have limit of, shoot, is it jumping? Going to the limit of n approaching infinity, n plus 2 over n cubed minus 1 divided by 1 over n squared, which is going to give us 1, bigger than 0. So this is convergent by limit comparison test. This one, if you again do limit comparison test, since what really matter is just there, it's just the highest power in the numerator and denominator, n cubed plus 1 over 1 over n squared, which is also going to give us 1. So it's also convergent by limit comparison test. How do you do NCT? Yeah, both of them. So does that answer your questions, Kevin and Carrie? Convergent. It's convergent, not conventional. How does it simplify to? Okay, sure. Give me a second. I'll write it down. Okay, we have limit of n approaching infinity, n plus 2 over n cubed minus 1 over 1 over n squared, right? You have limit of n approaching infinity, n plus 2 is 1 over n squared. So basically, you multiply n squared here, so you have n cubed minus 1. So did you see the the highest power? Yep. So you have like n cubed plus n squared over n cubed minus 1. So what really matters, n cubed over n cubed, which is 1. And you're gonna do the same thing over here, which is going to give us limit of n approaching infinity, n minus 2, n squared, n cubed plus 1, which is going to give us 1. So it's convergent by limit comparison test. Okay, so if we all good, I'm gonna end the sessions here, and I'll see you guys next week. Have a great week, guys, and have any questions, let me know.